Good afternoon. So Dr. Nitsche is away today, so I'll be continuing our lecture series. So, who remembers what we talked about last time? We talked about light. Correct. All right. We'll at least remember that. So we were discussing some different properties of light, and Dr. Nitsche spent a lot of time convincing you guys that light was a wave. We discussed how the waveform of light, is given by a wavelength, which is the distance between either two peaks or two troughs. And also that, as far as we're concerned, light has a constant speed. All forms of electromagnetic radiation have a fixed speed c, which is 3 times 10 to the 8th meters per second. We also talked about the frequency of light, which is related to the wavelength through this relationship. That is, the wavelength times the frequency equals the constant speed, which makes sense because if both of these waves are traveling at the same speed, you'll see a peak more frequently with the 400 nanometer than you will with the 700. Okay? And so we had this. We also were discussing polychromatic and monochromatic light. So the light that we see in the room that our eyes are sensitive to is the visible region. And when we have all of these frequencies, it appears white to us. And if we take a white light source and we put it through a double slit like this, we see the white two regions of intensity here. However, if we do the same experiment with a monochromatic light source, such as the laser, where we only have one wavelength, then we see this type of interference pattern with bright and dark spots. You remember when we projected it over here on the side, there was the red Heino laser that had the bright and the dark spots. And that comes from interference, which is a wave property. This laser pointer is another example of a single wavelength device. It's green, which is 532 nanometers. That's monochromatic. So as we showed these wave properties of light, we also talked about the electromagnetic spectrum. So we have this whole range of different types of light, of which all we can see in our visible range is this little chunk right here from 400 to 700 nanometers, which we call the visible because that's what we can see. If you look on the shorter wavelengths, or higher frequencies, we first get into the UV region, and the UV is what we most know from getting tans when we're out at the beach. Also can cause skin cancer if you get too much UV light. It can be damaging, but we can't see that. And then if you move farther in, we have X-rays, which, who's ever had an X-ray in here? Lots of people have had X-rays. Yeah, they use it to look at your bones because it can image through your skin. But we can't see X-rays. If we could, if our eyes had the rods and cones sensitive to X-rays, then I guess we'd be Superman, and we could see through things, and that would be cool, but not the way it is. Then we can move to even shorter wavelengths. We get into gamma rays, which you see in the cosmos. Now, if we move to the longer wavelengths, the first one we encounter is infrared radiation, which we know as heat. So any heat lamp that you have will usually be putting out infrared light. Again, we can't see infrared light, even though it's right next to our visible region. If we could see infrared light, then we would be like the Predator in our governor's famous 80s movie, The Predator, and its less successful sequel, Predator 2, starring Gary Busey. But there are certain animals, like there's certain types of snakes that have glands which are sensitive to infrared radiation. So it exists even on this planet. You don't have to go to Pandora to find stuff that sees different wavelengths. Yeah, Avatar reference, I've seen it. Then if we move farther to the IR, we get into the microwave region, which we all know from microwave ovens. It heats up our food, makes us ramen at 2 a.m. when we're doing Chem 1 problem sets, etc. And then we move into radio waves, which we of course know from listening to the radio, if you guys still listen to radio. Also, who here has ever had an MRI? MRI is a radio wave, so you lie in that big tube and you hear all those clicking noises, and like an hour later they image whatever ligament is damaged. That's also done with radio waves. So there's usefulness for all these parts of the electromagnetic spectrum, but all we get to see is visible. Now, we also talked about absorption and emission. So different solutions or molecules or atoms can absorb light or emit light. And this is an example of a continuous absorption spectrum. We see this here would be our wavelength range, starting down in the violet blue and going up to red. And then this vertical would be the intensity or the amount of absorbance at a given wavelength. And absorbance spectrums can tell us something about the color, because if it absorbs given frequencies of light, then we won't see those. All we'll see is what is not absorbed by the compound. So if we have here, we see this peak that covers sort of the blue-green region, a little bit of absorbance here in the red. So what color does it look like this thing might be? Orange, red, right. And we also saw, when we had the white light source with the diffraction grating up here and we put in the different colors of dye, we saw how it wasn't always just pure blue or pure, red that got passed by our solutions. It could be the different chemicals can absorb, slightly different parts. And, not all blues are created equal, not all reds are created equal. They can have different parts of the spectrum in there, and that's how we get from our Crayola 8 box to our Crayola 32 box, because there's lots of different shades of color depending on the exact absorbance spectrum. We also can have emission, and if we put enough energy into certain molecules, they can also emit light. And like, for example, here, this guy looks like it would emit in the blue-green and in the red. So we can also have line spectra, and what that is a thing which either absorbs or emits very specific wavelengths. So instead of having this whole broad blob of absorbance, we only have very discrete and very specific wavelengths that are absorbed. Lasers, again, are a good example of line emissions, because this guy only puts out 532, and 532 only. So depending on the identity of the substance, we can have continuous emission, we can have line emission, line absorption, continuous absorption. So let's do a chem quiz. So we have everyday glass, household glass. We have it back in the booth there, you have it on the car, you have it on your home. If I had a piece of glass up in front of me, would you still be able to see me? Wouldn't look funny, right? So let's think about what would happen. What would the absorption spectrum of glass look like? What wavelengths could it absorb while still keeping this transparent property of which we are well aware of? So let's see what we got here, minute and a half. We'll see. I think we had 255 people this morning. So we'll see how many we have today in here. Go ahead and vote. I think we can hit 250. More people would want to come in the afternoon, right? I don't want to get up at 9 a.m. 50 more. I don't know if we're going to make it. Come on. Oh, only 226? Don't forget to vote in. 227. All right, 228. Let's see what we got. A, B, C, one prankster with D. Oh, that's hilarious. Trust me, it gets less funny every lecture. All right, well, still have some discrepancies here. Let's talk about it and vote again in a second. Let me tell you one thing. The visible absorption, right, is all the way between the UV and the IR, right? Or visible covers this whole region. UV is down here. Visible is in the middle here. This is the center of the visible, but it covers this range. And then IR is up here. Okay? So this whole area in here is visible. That's UV, and that's IR. Let's talk with our neighbors. Vote again here eventually. Let's see if we can come to some sort of strong consensus. "20 seconds. Don't forget to vote in." Five seconds. Okay, let's see what we got. Yes, all right. Moving in the right direction here. I will clarify so that we can all get to the same page. I guess that hint helped. The morning class told me that they were a bit confused by the plot, so try and clear it up here. But let's move on to the answer. So, as I said, we have our whole visible range here, and we've got three different absorbance curves. Oh, well, it's one. So the way that this works is for 3, we can see that 3 is going to have some absorption in pretty much the whole visible range. So we won't be able to see through that because any visible light is going to get absorbed by that material. So it's going to be a very dark black plexiglass. I guess wouldn't really work well as a window because you wouldn't see through it. Number 2 here, we can see onsets around the green-yellow range here and is going to absorb most of this blue-violet. So what color would it look like in that window? If it absorbs all this blue, what's it going to look like? Pinkish, reddish, yeah, on the red end of things. So while it might be cool to have red windows, it would look kind of weird going out there. But our windows that we usually use are, yes, number 1, because there's no absorption in any of the visible wavelengths, only the UV wavelengths. So it looks clear to us since we can't see ultraviolet light. Now this is why you can't get a tan sitting in your car, because all the UV light is going to get absorbed by the glass. That's why also if you have the transitions lenses or whatever that turn dark out in the sunlight, those won't work in your car because the UV already gets absorbed by the lens or by the glass before it gets to the lens. So that is all we have about our wave properties of light, I believe. So that's what Dr. Nitsche used a lot of yesterday. But what I am going to try and convince you of now is that light is actually a particle. That's what I'm going to try and convince you of today, and we'll see whether you believe Dr. Nitsche or whether you believe me more. We'll find out at the end. So, let's start with the black body experiment. So around the 1900s, the scientific community was pretty convinced that they had a really good grasp on the way the world worked. There weren't a lot of brand new phenomena that we hadn't already observed, so it was all just refining the details. One of the problems that they were trying to explain was a radiation emitted from a black body. What a black body is an ideal system that does not reflect any light. It absorbs light and then re-emits. So you can put heat into it and look at the emission that comes off, but it's not going to reflect light. That's why it's called a black body. And in, I believe, 1894, there was a German by the name of Max Planck. And Planck was trying to solve this black body problem. And there have been a few scientists who had attempted to tackle this before, but none of their theories would match the results that you see. So an example of a black body, or something that works kind of like a black body, would be, say, the heating element on a stove. How many of you have an electric stove? Electric stove, anybody? I don't like electric stoves. But an electric stove works by putting a current through this element, and if you jack that thing all the way up to high, you'll notice it starts glowing in the red, right? Which is about as hot as you want a stovetop to get. But if you were to continue to heat this element, say you were a blacksmith and you wanted to forge a sword or horseshoe or whatever blacksmiths do these days, you heat up that metal in a furnace, it starts to glow white, right? It's like white hot, and then you can pound the metal. Also, if we remember the old school tungsten filament light bulbs, they also work this way. You just have a piece of tungsten and you run current in it to heat it up, and when it gets warmer, it starts emitting and glowing in the white. Now we use the fluorescent lights now because they're more good for the environment, and Al Gore doesn't want us to make greenhouse gases, but that's besides the point. They're a black body. But the phenomenon that they observed, that Planck and others observed at the time, was that if we started at, say, 1300 Kelvin, we would have this maximum in intensity right here. Now, as we increase the temperature to 1800 and then to 2000, the maximum in the intensity not only shifts intensity, it also shifts wavelength. So we can see it shifts to shorter and shorter wavelengths as we increase the temperature. And this couldn't be explained by the laws of physics that they had derived at the time. And so Planck was looking at some of these things, and he was trying to figure out a way to make this work, and he said, well, what if, I want the curve to fit, we want it to be right. So what if I treat this energy emission coming in discrete packets? Instead of having any value, it has to have, there's some smallest unit that it has, and everything that it emits comes in multiples of that unit. Integer multiples, where the integer is 1, 2, 3, 4. Can't be a half, can't be 0, can't be 3/4, can't be the square root of 2. Got to be a whole integer of this packet of energy. And this packet of energy here is h nu, where h is a constant and nu is the frequency. And this wasn't uncommon approach. There was a guy by the name of Boltzmann. Who's here heard of Boltzmann? You will. Boltzmann did this in a lot of his derivations. He would say, treat energy as coming in some sort of packet, so he could work the math to get a solution, and then at the end he would require that that energy packet size go to 0, so that it still obeyed what, the physical observations that they made. Well, Planck did the same thing. He said, I'm going to treat the energy coming in packets. But then he didn't set it equal to 0 again, which, as it turns out, had profound implications for the beginning of the study of quantum mechanics and modern physics. And I believe that Planck would justify saying, oh, well, it's just a mathematical interpretation to make this sort of theory work. Really, we know that energy doesn't come in packet size. We can have any value. But he got his constant, which is Planck's constant, 6.626 times 10 to the negative 34 joule times second. You know the guy is important because if you have a constant named after you, you probably did something pretty big. And for his description of the black body problem, Planck was awarded the Nobel Prize in 1918. So that was all well and good, and then, okay, we've solved the black body problem. But let's move on here and let's think about light in another way. So if we have a light source with a given intensity I naught, let's say we put a filter that cuts the intensity in half. So after that, we have half the intensity. Well then, what if I put on 2 of these half-intensity filters? Then I get down to 1/4 of the intensity. And what we're getting at here, if we keep cutting it in half and keep cutting it in half, do we get to a point where there's some sort of fundamental unit of light if we cut it small enough? Well, if we cut it in half each time, can we ever get it to some smallest bit that we can't do that anymore? And it's like, if you think about, you remember on I can't remember whether it was the first day or the second day of lecture where Dr. Nitsche had the block of 55 moles of carbon, sort of this little cylinder. So let's say, imagine we had some sort of nano cutting device, and we were to cut this thing in half and cut it in half. Eventually we would get down to the point where if we cut it in half each time, we would get to 1 single carbon atom. And if we have 1 single carbon atom, we can't cut it in half anymore, because then it won't be carbon anymore. If I cut carbon in half, from 6 to 3, by my math, that becomes lithium. So it is then no longer carbon. So the fundamental unit of carbon is 1 atom of carbon. So what we're trying to get at here is, can we get there with light too? Is there some fundamental thing that is a light that we can no longer subdivide or decrease in intensity? There we go. So if we have a flashlight and we put in a bunch of filters and we shine our light on it, what's going to happen? Well, as it turns out, our eyes are really sensitive to light. We can see very dim sources from very far away. So if we had a really, 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 really dark room that we were shining through all these filters before it got in that room, what would we observe? Well, we would see little flickers of light getting through. So it's almost as if there's some sort of fundamental particle, if you will, of light. And that's what we call a photon. Who's heard of a photon before? Heard of a photon? Do you know who coined the term photon? G.N. Lewis. You know where G.N. Lewis was a professor? Right here in Berkeley. Now, as it turns out, the paper in which he coined the term photon was all wrong, but the name stuck. So that's what this was, I think, 1926 when Lewis coined the term photon. So it was a while after Planck, right, we got to describe this light as being a photon. You know where photon comes from? It comes from a Greek word, which is phos, for light. So Greek for light, that's where photon comes from. And this photon has an energy that is equal to Planck's constant times the frequency. So now we can see this relationship between frequency and energy for this fundamental bit, this photon of light. Come on. So, having this fundamental bit of light gets us to the photoelectric effect. This was another phenomenon that was noticed by people doing science around the turn of the century. Basically, if you shined light onto a metal, for certain wavelengths, that metal would emit electrons. And for certain wavelengths, it wouldn't emit electrons. And scientists tried things like, what if we change the intensity? Then can we get, electrons from different wavelengths? And what if we, measure all these things? This is what they're trying to understand how this photoelectric effect works. So what happens is, say we shine red light onto this metal. Nothing happens. Exciting. But let's say we move up to green light. If I shine green light on this surface, all of a sudden, I get electrons coming off. And if I shine blue light on the surface, I get electrons coming off, and they have more energy. Now, we can measure these electrons through various devices that measure currents, and current is something that's very easy to detect in very, very small numbers. So that turns out to be a good thing for doing science. And what people observed at the time was that no matter what intensity of red light they would shine on this metal, they wouldn't get any electrons off. And no matter what the intensity of, say, blue light they shined on the metal, the electrons would all have the same kinetic energy when they came off. And this didn't mesh with classical physics at the time, because according to classical physics, if you put a bunch of red light, it should put in enough energy in there to eventually kick off an electron. And if you put a bunch more, then they might come off with a spread of energies. And so this didn't work with physics, and this was confounding at the time, until in 1905, a Swiss patent clerk by the name of Albert Einstein, you may have heard of, he wrote a paper on the photoelectric effect. And what he did was use, sort of inspired by Planck's treatment of radiation from the blackbody problem as a quantized unit, right, this packet of energy, quantized, which comes from the Latin quantum or quantus, which is how much. Using this idea of energy quantization, he used what he called a light quanta to describe this photoelectric effect. And even people such as Planck thought that Einstein was wrong, that there's no way light can come in quanta. Light comes in waves. We've known since the 1600s that light was waves, so how can it all of a sudden be a particle? And so this was a big, sort of paper at the time to use this light quanta to explain the photoelectric effect, and he got it right, which was the confounding part about it. It was correct, the theory was correct, it matched the experiment, but they didn't think that that was the way that the world worked. So what I have here is this is a plot of electron kinetic energy, this ejected electron's kinetic energy, and this here is the frequency of the light. And so what you can see is, at this point, any frequency shorter than right here in this whole region is not going to eject an electron, no matter how much intensity you have. There's a difference. Intensity is sort of how many photons you have or how many waves of light you have, and frequency is the color. So you can have the same color and change the intensity, right? So these are two different things, intensity and wavelength or frequency. And this cutoff threshold would be called what's supposed to be a nu. It's nu naught. There's some frequency at which all of a sudden we start kicking off these electrons. Now, again, if we go back to Einstein using this concept of a photon, again, Einstein didn't use photon. This was 1905. He called it light quanta. It took G.N. Lewis in 26 is where photon came from. He said, all right, well, what if this photon has energy which is equal to Planck's constant times the frequency? If I have red, no matter how many photons of red light I have, there's not going to be enough energy in one of them to kick off the electron. The other important thing that Einstein sort of worked towards is that the photoelectric effect is an interaction between one photon and one electron. You can't have a bunch of photons kicking off this electron. He said, well, it's one photon, one electron. Now, what was this portion here, this amount of energy that you have to put in until you can start to kick off electrons, is called, it's a phi, it's called the work function. And that's the energy it takes to remove an electron from the metal. Because we know electrons are negatively charged. The nucleus is positively charged, yes. So there's some sort of attractive force there that holds the electron orbiting the nucleus, right? Because otherwise it wouldn't stay there. So you have to put in an amount of energy equal to that force in order to remove the electron. Then any excess energy that you have that electron takes from the photon then becomes kinetic energy, which is why we have increasing kinetic energy with increasing frequency, because if we put more and more energy in, but this work function is a constant, then we have more energy left over to go into the kinetic energy of the electron. So we could describe this threshold frequency here has an energy equal to h nu naught. And that's going to be the energy of the shortest frequency light that will just remove that electron from the metal. And then h nu is our initial photon, so the difference will be our kinetic energy. So we can see that if our frequency here is less than this threshold frequency, we would have negative kinetic energy, which doesn't make sense. And that's good because we don't eject electrons there. Now, not all metals are created equal. So we can also have, I suppose I should do that first. So we can also think about this work function as like a well. My electron is trapped down at the bottom of this well, and it's got to climb out if it wants to escape. So if I have my red photon here, it has energy less than this work function, so it can't get out of the well. It's stuck down there, and it's not going anywhere. So we don't see this electron coming off. But if I move to green now, I'm above this threshold. So it's able to get out of the well, and then it's still got a little energy left over that it can sort of go and do what it wants with, right? This sort of green here, just above this threshold frequency. And if I put blue, that just kicks the thing way the heck out of that well. And it's got a ton of kinetic energy to work with. Okay? So that's how this was explained by Einstein, and we also have different metals can have different work functions. So if I have a metal 2, which is shown here, we can see that it has a higher threshold frequency. So it takes more energy to remove that electron. And so for this given frequency, right, if the threshold frequency for metal 2 would be enough to kick off an electron from metal 1 with a pretty good kinetic energy, but on metal 2, it just barely removes the electron. So the identity of the metal as well as the frequency of the light are important for understanding how this photoelectric effect worked. And this was kind of a big deal in the progression towards modern-day physics and modern-day quantum mechanics, and it was this that won Einstein the Nobel Prize in 1921. He did not win a Nobel Prize for his theories of relativity, which everybody probably knows more about or has heard more common, but it was the photoelectric effect that got him his Nobel Prize, and that's when he really became on the scene as a prominent physicist of the early 1900s. Yes?
If you were to take the red light that you emitted to a piece of metal and you put it on a different piece of metal, would you get electrons released?
It depends on the work function of the metal.
So what is it that makes that red not emit any electrons?
Because the red wavelength, right? So this red light, its frequency is down here. It's got a lower frequency than the green, so it doesn't have enough energy in it to remove this electron from the metal.
But if we put it with a different...
But a different metal we could have a metal with a lower work function, then that metal might be able to have red light knock off a photon, or knock off an electron. It depends on both the work function of the metal, the identity of the metal. Every metal is going to have a different work function, so it's going to have a different threshold frequency, so different colors will be able to emit it. I only got 15 minutes. We better book here. Okay, let's try a chem quiz. So we shine a beam of light on a metal. Bam. Nothing happens. If we want to kick off electrons, what's the best thing to do? Increase intensity, decrease wavelength, or increase the energy? Let's go ahead and, I didn't want to do that. Let's go ahead and vote. What do we have, 226 the first go? Something like that. See if we can get to 230. Some late arrivals, maybe. Six more. Come on. 4. 3, 2, almost. Come on, give me 230. Oh. All right, let's see what we think. So we have a fair division between B and C. There's some people that seem A, and I see our pranksters are back. All right, well, let's do a demo. Let's get Karen to help me out here. Let's see if we can get to a consensus on this. So I've got my basketball. Let's say my basketball is like my electron. And Karen is my metal. Turn around. So I want to knock that basketball off of her. So let's say I start with the small stick. This isn't very big. This doesn't have very much energy, does it? So if I get her with that, this is not going to work. I can't hit her hard enough with this to get her to let go of the basketball. So let's upgrade. Let's upgrade to this meter stick. It's a bit bigger, a little more mass here. If I swing it at the same speed, it's got some energy, right? So if I get her with the meter stick, just enough to knock that basketball loose, but it's not going anywhere. Well, that's no fun. I want that basketball to fly. So we got to get the big dog out. This 2x4, I think we would certainly agree, is a lot bigger than that meter stick. And so if I get her with the 2x4, bam, that basketball's gone. Right? I'm swinging them all the same speed, but this guy, which is bigger, has more momentum and more energy to impart. So you can see with this guy, no matter how many times, I could sit here all day wailing on Karen with this little stick, and that basketball ain't going anywhere. Right? So no matter how intense I get, it's not going anywhere. But with the big dog, all I need is one, bam, and the basketball is gone. Because it's a one-to-one interaction, one photon, one electron. So, going off of that, let's talk amongst ourselves and see if we can come to a consensus here. Go. All right. So intensity is sort of like how many photons you have at a specific wavelength, or how many waves you have at a specific wavelength. But it doesn't change the wavelength, right? So you can have a ton of photons that are red. They're all going to have the same energy, but they're not going to have the same, but you can have more or less of them, but they all have the same amount of energy because they all have the same wavelength. So intensity is different because it's sort of like how many. Are we done? All right, let's see what we got. Are we sheep or are we sharks? Oh, we got some sharks out there that are committed to their B, and they've managed to bring over some of the C's. We still have our two guys who are off in left field. Oh, so funny. All right, well, for the sake of argument, let's see who's right. See, is it the B's or the C's? Well, We got to have more energy to kick off the electron, right? Remember the well? If we don't have enough energy in our photon, it's not going to get removed. So we have to give it more energy. We know that our energy of our photon is h nu, and we remember from the earlier slide that nu times lambda is the constant speed of light, so c over lambda is nu. So we can see that energy goes up, wavelength goes down. So we got to increase energy, right? So it's C. Or B. Ha ha! Chumps! Gotcha. They're both right. So B and C are both correct, right? Stick with me. I still got 8 minutes. We see that energy and wavelength are inversely related. So decreasing the wavelength is the same thing as increasing the energy. So one more chem, because let's see if we can get this on the first go. So remember we were talking about different metals and different work functions. So I've got metal 1 and metal 2. They have two different work functions, right? Which is the amount of energy it takes until electrons start getting emitted. We got kinetic energy of the electron here, frequency here. Which combination of a photon striking a metal ejects an electron with the highest kinetic energy? A yellow photon on metal 1, where's yellow going to be? Somewhere in here, somewhere between red and green. So a yellow photon with curve 1, a green photon with metal 1, or a blue photon with metal 2. Uh-oh. Two variables. Well, let's see if we can get this on the first go. Which one of these is going to have the highest kinetic energy, right? Highest kinetic energy. Let's vote. Uh-oh. Different wavelengths and different metals. Which one is it going to be? So we remember, right? Oh, you can't see it. It's sort of hidden behind here. Right there. H nu minus the work function, right? Or H nu minus H nu naught. That's what we need. Which one is it going to be? 45 seconds. We're halfway home. $11 more. Don't forget to chime in. I hope people haven't left already. We'll see. 10 seconds. Which combination is it going to be? All right. Let's see what we got here. Yes! I'll take that. I will take that. So that looks pretty good, 69%. Think B. Let's look at this. Okay. So what's it going to be? We got yellow, green, and blue, but the two different metals. So we start with yellow. The largest yellow would be around here. So what we do is we trace up, and we see that, okay, here is our kinetic energy, right? For yellow, right here. But if we move over to green on metal 1, oh, it gets higher up on this electron kinetic energy. We get more kinetic energy here for green than for yellow. Now we know that blue has the most energy, right, of these photons. However, because metal 2 has a higher work function, it takes more of the energy of that photon to remove the electron from the metal, which means we have less left over to go into kinetic energy. So we trace up here. So in fact, the blue on metal 2 will have the least amount of kinetic energy for the three. Now, what about if it were, can I do blue on metal 1? Sure, why not? But this curve would keep going up here, so blue's somewhere around, up here-ish, so its kinetic energy would be off the charts. So if I put blue on metal 1, it would have the most kinetic energy, but since metal 2 has a higher work function, right, I've got a set amount of energy in that photon. I take away the work function of the metal, and then what's left over is the electron kinetic energy. Okay? So it was B, green, metal 1, most kinetic energy. So now, we've had Dr. Nitsche's lecture on the wave properties of light, with our wavelength and our particle, and I've been trying to convince you that it's a particle. So is it a wave or is it a particle? Why not both? And really the solution is just that simple. There are particle properties and there are wave properties of light, and depending on the experiment, you can observe either one or the other. Now, the person that came up with a relation to relate between these was a French scientist by the name of Louis de Broglie, or Louis de Broglie, however they pronounce it. And what he said is, okay, if I've got a particle, we have an associated momentum to describe the movement of that particle. For a wave, this wavelength will describe the properties of that wave. So if we want to relate these, we use the de Broglie relation, which is the wavelength is equal to Planck's constant divided by the momentum, or vice versa. The momentum is Planck's constant divided by the wavelength. So in reality, there's this duality between wave and particle properties of light. Now, while this debate was going on, there actually have been experiments that have confirmed the particle nature of light beyond Einstein's hypothesis from his photoelectric effect. One of these experiments was the observation of Compton scattering of X-rays. Compton scattering is named for a scientist by the name of Arthur Holly Compton. Now, Arthur Holly Compton is important to me because my undergraduate university, the College of Worcester, was also Arthur Holly Compton's undergraduate university. So, College of Worcester enrollment 1800, we have one Nobel laureate from our alumni. We don't have as many as Berkeley. I know you guys got Nobel laureates right and left. All we got is Arthur Holly Compton. So Arthur Holly Compton's my boy. You should look, if you look up Compton scattering, looking at an X-ray scattered off an electron and confirmed that light has particle properties. Compton won the Nobel Prize in, I want to say, 27. Arthur Holly Compton. You look at Nobel Prizes in the early 20s, late 19 teens to 1920s, a bunch of the experiments that led to the formation of quantum mechanics. And so we'll move on with this exploration on Friday. Thank you for your attention. You are free to go.